Okay, let's get into this. We're doing a deep dive today on factorization.
Yep.
We've got the source material here. It's like a guide to breaking down algebraic expressions.
Right.
And our mission, really, is just to pull out the key methods, the stuff you really need to grasp.
Exactly. Think of factorization like working backwards with a recipe.
Okay.
You've got the final result, the expression, and you want to find the original ingredients, the simpler bits that were multiplied together.
Right, the ingredients, those are the factors then. The source says factors are just what you multiply to get the expression.
That's it. Like 5 and x are factors of 5x. Pretty straightforward.
Or the slightly more complex ones.
Yeah, like 2 by 5 and 3x plus 2. Those are the factors if you multiply them out.
Okay.
So factorization is just starting with that result and figuring out, what made it, finding those original factors.
Got it. So first method, where does the source say to begin? What's the first tool?
Always start by looking for common factors. Taking out common factors is what they call it. You scan the whole expression, find the biggest thing, number, variable, combination that divides into every single term.
Ah, okay. The source has 5 by x had 10x.
Right. So you look at the numbers 5 and 10. Well, 5 goes into both.
Yep.
Then the variables xx and x. The highest power of x that goes into both is just x.
So put them together. 5x.
5x is your greatest common factor. You pull that out front. Then you ask 5x times what gives you the original terms.
Okay, so 5x times x gives 5 base out. And 5x times minus 2 gives negative 10x.
Exactly. So you get 5x, then parentheses x2. Done.
So check that first.
Yeah.
But what if, not every term shares the same factor?
Good question. That leads us to the next technique, usually factorization by grouping.
Grouping, okay.
This often works when you have, say, 4 terms. You try arranging them into pairs.
Yeah.
Pairs that do share common factors.
I hope something clicks.
Kind of. The example is x bx plus a by.
Right, 4 terms.
So you could group the first 2, x bx, and the last 2.
Okay, I see. The first pair has x in common.
Yep. Pull out the x, you get xab.
And the second pair has y.
Pull out the y, you get yab. So now your expression looks like xab plus yad.
And now AB is common to both of those chunks.
Precisely. That's the goal. So you factor out the common binomial, AB.
Leaving you with AB times x plus y.
AB, x plus y. It's like shuffling things around until a bigger common factor reveals itself. Pretty neat when it works.
Definitely. Okay, so from grouping terms, the source moves to specific patterns, things to just recognize.
Yeah, pattern recognition is huge in factorization. The big one is the difference of 2 squared.
That sounds familiar. X, say, y-o.
That's the one. If you see something squared minus something else squared, it always factors into x plus y, xy.
Yeah.
Always.
So if you spot that pattern, you can just jump to the answer.
Instantly. Like the example of 4 by sub n 9. You need to see that as
2x minus 3.
Exactly. So boom, 2x plus 3, 2 by 3.
Nice. And 25a, 36b.
Same idea. That's 5a minus 6b.
So 5a plus 6b, 5a, 6b.
You got it. Spotting that saves a lot of work.
Okay, moving on. The source talks about trinomials, 3 terms. The example is x are 9x plus 20.
Right, the classic quadratic trinomial. The common method here is often called splitting the middle term.
Splitting the native at 9, how?
You need to find 2 mystery numbers. These numbers have to multiply to give you the same product as the first and last terms.
So x out times 20, which is 20 max order. Well, just 20 for the numbers.
Right, product is 20. And those same 2 numbers have to add up to the coefficients of the middle term.
Which is neg 9.
Yeah, so multiply to 20, add to negative 9. You might need to think about pairs of factors for 20.
Let's see. 1 and 20, 2 and 10, 4 and 5. To get negative 9 has to be minus 4 and negative 5.
Perfect. Negative 4 times minus 5 is plus 20. Negative 4 plus negative 5 is negative 9.
Okay, found the numbers. Now what?
Now you rewrite that middle term, negative 9x, using those numbers. So the expression becomes x sub 5 by 4x plus 20.
And now it has 4 terms.
Exactly.
Which means?
You can use grouping, like we just did.
You got it. Group the first 2, x, x5. Group the second 2. Be careful with the sign. Pull out negative 4.
So negative 4 by 5.
Right. Giving you x by 5, 4 by 5.
Right.
And now, the a5 is common. Factor it out. I5 by 4.
And that's it. So factoring trinomials often turns into a grouping problem once you find the magic numbers.
Makes sense. Okay, last thing the source covers seems to be factorizing completely.
Yeah, this isn't really a new method. It's more of a reminder. Keep going until you can't factor any further.
You might need multiple steps.
Often, yes. You combine the techniques. Look at their example. 8 by a has to my s by pass.
Okay, first step.
Always. Look for common factors.
Right. Numbers 8 and 18 divisible by 2. Variables x, hexate, and psycho, common factor is x. So 2x.
Pull out 2x. What's left inside?
8 minus x divided by 2x is 4x. And negative 18 minus psi is divided by 2x is negative 9y. So 2 by 4 by 4 by has 9y.
Good. Right. Now look inside that bracket. 4 by 9y ACUS. Does that look familiar?
Wait. 4 by second is 2x fine. 9y hattie is 3 by high. It's the difference of two squares again.
It is. So you apply that pattern now. The 2x stays out front.
And the 4 by side is 20y becomes 2x plus 3y, 2 by 3y.
Put it all together. 2 by 2x plus 3y, 2 by 3y. Now that is completely factorized. Nothing else can be broken down.
Wow. Okay. So, quick recap then. We've got pulling out common factors first, always.
Always.
Then maybe grouping if you have 4 terms. Spotting special patterns, like the difference of two squares. Splitting the middle term for those trinomials, which leads back to grouping.
Usually.
And finally, just keep applying these tools until everything's broken down as much as possible, factorizing completely.
That's the toolkit, basically. Methods to break complex expressions down into their simpler, fundamental building blocks, just like the source lays out.
It really is about taking things apart to understand them better, finding those core components. It makes you think. If you get good at this, at seeing how complex math structures break down into simpler parts, could that skill, that way of thinking, help you tackle complex problems elsewhere, like in your work or just life stuff?
Yeah.
Breaking big challenges down into smaller, manageable factors.
That is actually a really interesting thought. Deconstructing problems.
Yeah.
Something to ponder.